doing this, feel free to jump in. And I intend to publish this in the newsletter, so you don't have to take notes, and there's no test afterwards.
Thank you. That's perfect.
So this is an image I took of M51 with some modest equipment in out west in King County a few years ago. And I'll discuss the techniques I used to get that image, both the little mechanical and then also with the software. So the deep sky imaging process, this first column is the mechanical part. So obviously you need the telescope focused, mount, balance, and polar aligned, go to calibration and find your object. Make sure the camera is safely attached, and with the telephoto lens and with the telescope, make sure it's focused properly. And the environment, what's your weather like? Do you need dew control? What are the sky conditions, which we talked a lot about today? What's the phase of the moon? Because that may affect what objects you pick and also what kind of exposure time you can use. And then what objects are available that night versus just going out there and say, hey, it's summertime, I want to do M42. Well, that's not going to be up for a few months. Electronic, you want to make sure you have reliable power to the equipment, whether it's battery or AC. Make sure your computer is set up properly and running, and then get all the wires and cables in good order and try to protect it so you don't trip over everything while you're out there in the dark. And then also with the software, image acquisition and guiding software working properly. And all of these things should be done well before you go out, and also like rehearse it at home, rehearse it in your house at night in the dark, and make sure you know where everything is and all that. So the better prepared here, the better imaging you get. On this right-hand column, this is going to be talking about image acquisition and processing, and this is mostly what we'll talk about tonight. So on the acquisition side, you want to know if your camera cooling is working, or if you don't have camera cooling. Take your dark frames. You want to do guiding calibration. Select the filters you want to use that night, and that'll affect when and where you're going to take your objects, so you have enough time to go through all the filters at night. Duration and number of light frames, there's several factors that involve that decision. And are you going to do color images or black and white? And then for processing, you want to make sure you take the light frames, get the image calibration going where you have the dark subtract, the flat frames, bias frames, flat darks. And we'll concentrate on those tonight as far as definition and what they're used for and how they're used. And then SNR, that's the big thing, signal to noise ratio. So through all of this, you want to produce the best signal, what you want to keep, to noise, what you don't want to keep, ratio. So that's a lot of what we're going to talk about tonight, is that signal to noise ratio. So the signal is the count of photons reaching a sensor. Any kind of photons, right? Noise is the random variation in the signal. And then the SNR is signal divided by the noise. And by collecting more photons in longer exposures or stacking images, you increase the signal to noise ratio by the square root of the number of exposures. So for example, a single exposure has a quality of 1. A stack of 16 exposures will make that image 4 times better, just because of the ratio of signal to noise. So what are some of the main factors in the decision making? Because you have to figure out how long, what duration your light frames are going to be. Because that'll tell you then how long your dark frames have to be. So sky conditions, if it's a hazy night, focal length and ratio, do you have a long focal length or a short focal length, like an f10 versus an f4? And that would be also, the f-stop on the DSLR. How good is your guiding and tracking? So how long can your light frames be? Like Andy said, he's only shooting 3 minutes now because of the conditions, and normally he shoots 5. And then what is the subject? So a star cluster will be a different set of light frames than a globular cluster or a planetary nebula, galaxy nebula. Normally, like a globular cluster is a very concentrated area of signal and then a lot of non-signal or sky around it, versus a nebula, which the whole frame could be filled up with signal. So there's all these things to consider. And also there's an effect of the sky background noise. So object photons and sky photons are both recorded. And a real dark sky will have a high ratio of object brightness to sky background. Just as you look visually, right, you can see the faint galaxy or the faint nebula out at a dark side versus in near Chicago. A good suburban sky will have a lower ratio of the object brightness to sky background. So considering imaging, it's necessary to accumulate more total exposure time under a bright sky because you want to increase the signal versus the noise. So if you take a single frame of, like Andy did with M81, M82 versus 20 frames, you're going to get a bigger ratio of that signal to noise with the 20 frames. So here's my setup. And the reason I'm showing you this is that when you take your calibration frames, such as the flat frames, which we'll get into, you need to have this whole system in the same configuration as when you take light frames. And so I built this cradle to hold my camera onto the telescope, and it's all on a single plate. So during the observer or imaging session out at the field, I'll take dark frames with this, but I'll take all my other calibration frames the next day. And I can do that because everything is fixed here. I'm not taking it apart. And also, when we talk about the flat frames, you'll see how many surfaces the light passes through. So it comes in, bounces off the mirror here, goes off the secondary, goes through the tube. Then I have a focal reducer here. And then the camera itself, there's a focal reducer. Then I have filters in the filter wheel. Then there's a glass pane, and then the sensor itself in here. So there's lots of surfaces that the light has to pass through. So here's my image acquisition summary. So I get the telescope mount, calibrate it for guiding. And then while it's guiding, I take my dark frames so that it has at least 5, 10, 15, 20 minutes of guiding. And then I take the 10 120-second light exposures for each of the 4 filters. And then the next day, I'll take the set of flat frames and bias frames with the whole setup the same, with the temperature the same as I took during the light frames. So here's some definitions. So what is a dark frame? So the dark frame captures a sample of the dark current, which contains the thermal electrons that accumulate during the time an image is created. So the dark frame is taken with the same conditions as the light frame. So when you take a light frame of 5 minutes, you're accumulating 5 minutes of signal, but you're also accumulating 5 minutes of dark current that's inherent in the camera. So when you're left with a light frame that has both dark current and light frame, you can subtract out the dark current, and then you're left with the signal. So that's that signal to noise ratio we talked about.
Mark, could I interject here a second?
Sure.
I think this is, for those of us starting out, usually with a DSLR, this is especially important to dark frames. It's important to, cross your camera line, but with the DSLR, especially when in the warmer weather, you get a lot more thermal noise. And by taking the darks, you subtract out that thermal noise. And, and of course, the hotter it is in the summer, the more noise you're going to get. So it's really quite important.
Yeah,
and I touch a little bit about some more details in a couple slides from now about that as well. But yeah, that's one of the things that you could take that dark noise out with software, but you're also taking out signal at the same time. what the processing software will do is take the dark current, subtract the dark current out, and not affect your light frame signal. The second set of frames is bias frames. So there's readout noise every time an image downloads. So you can take that noise out. Flat frames, they record the response of the entire optical system. So the telescope, the filters, any glass, it goes through a window of cover glass, and the CCD itself all leave residual traces, and you'll see that when I show you an example of that. The duration of the flat frames are usually a relatively short exposure, about 30 to 50% of the max pixel value. And I always mess around with that each time I do it. And when I get a good exposure for a flat frame, then I take like 20 or 30 of them and then average them together, median value, and then that becomes a master flat frame. The flat frames also produce dark current, so you want to take a dark flat frame for the same duration as the flat frame. And I have a diagram to show that a little bit later. So how do you shoot darks and flats and bias frames? Well, dark frames are relatively easy. You cover the telescope or the camera lens, or close the CCD shutter and cool the camera to its operating temperature, or in the case of the DSLR during the evening, record when you take it, because for the DSLR, you may want to take several series of dark frames throughout the imaging session, or take auto darks. And then take 5 or more dark frames, average them to remove the random variations. Now, each software processing has a different way of doing that, and I'll show you some examples of that later. But this is where I'd like to have, like Dan and Jim and Andy and Mark jump in for the different software that you guys use. Because I use AIP for Windows, obviously, that's different than the other ones. So dark frames can be taken at any time during the night or the next day, as long as it's the same setup. Again, it's the temperature that is the critical part of that. So like Andy mentioned before, the DSLR can heat up during the summer more than the winter. And Mark Christensen pointed out that a lot of that heat is from the battery. And so you may want to pause your imaging during the evening and let your DSLR camera cool down.
Yeah, and follow up on your point, Mark. In my experience, there's two major sources of heat in a DSLR camera that show up in the images. The first is the so-called amplifier glow, which the manufacturers are getting better and better about eliminating, because the heat coming off the amplifier that actually amplifies the signal from the individual pixels, that heat is all wasted energy. And they're desperate. They're always trying to reduce the power consumption of these cameras. So the so-called amplifier glow, which typically shows up in one of the corners if you take a dark frame, they're trying to reduce that problem. The second major cause, and it's often the dominant cause of heating in DSLRs, is the battery itself. As the battery discharges, particularly lithium ion, as the battery discharges, it generates heat. So one way to eliminate heating of the DSLR is to use an external battery pack. And very often that's the way to go anyways, because usually the batteries that are in the DSLRs don't last very long. When you're talking 5-minute exposures or 3-minute exposures and taking 10 of them, very often the batteries die. So if you're taking longer exposures with a DSLR, you really ought to look into getting an external battery for multiple reasons.
Thanks, Mark. And then bias frames are 0 exposure time with no light. So you cover the telescope camera lens, cool the camera to operating temperature, and take the shortest exposure your camera allows. So basically that's the readout noise. So what you're trying to do is eliminate all this noise from your image. So flat field frames. You shoot an image of a featureless subject, and the flat must be taken with the exact setup as used for imaging. It must be an exact record of how light passed through the optical system when the light images were taken. So if you have a camera that you can change the attitude of it, or what am I trying, orientation of it in your eyepiece. If you change that later on and take a different subject, you know, because you want to frame the nebula or whatever a certain way, and you try to apply flat frames, a single set of flat frames to both of those images, things won't line up as far as the vignetting or the dust donuts or things like that. So how do you take this? You place a white t-shirt over the lens or the telescope and shoot 10 to 15 flat frames, and then cap the lens and shoot the same number of flat darks at the same exposure time. And you can play around with that. And there's tons of instruction for that online of how to do other things, how to do things differently, I should say. And there's other methods. You can build a light box or take twilight flats or dome flats. This is the method I normally use, is put something over the end of the telescope or the camera lens. So here's an example of a light box somebody built, and they have an LED light with some diffusers, and you put your telescope or lens in from this side. So here's some examples of calibration frames that I've used. So I'm basing it on my 120 seconds of light frame that I'm going to use. Here's a dark frame, a single dark frame. And you see there's a pattern in there. There's like, maybe you can see a little crosshatch pattern, you know, larger. And then of course you have all the other little things going on in here. And then of course you have this amplifier noise. And then here's a bias frame that's 1/10 of a second. So this is the readout noise. So this is the inherent noise produced by a CCD camera or a DSLR. The dark frame is the same duration as the object image or the light frames. And the bias frame is the length of time that the image takes to download from the CCD to the computer. So this noise is subtracted from each of the object images. Here's an example of flat frames. So for that M51, I took blue, green, and red filter, and also with no filter, clear filter. So I took a set of flat frames through each of those filters. So this is the imperfection of the optical system. And this information is divided out of the light frame. Now, if you don't do flat frames, you can go in and through software get rid of this stuff, but it also takes away signal. What the software will do, and I've seen it in Deep Sky Stacker and Sequitur, you name these frames that they're flats, and it does the work for you. So you can see, like, here's the shadow of the center of the mirror. Here's the vignetting. Here's a bunch of dust donuts. Here's a little one. Here's a bunch of big ones. So all these things in here contribute to the light frame that you take. But this is noise, not signal. So there's different ways to calibrate. One is basic calibration. So if you're just starting out, this is fine to do, the basic calibration. You make several dark frames. Dark frames are combined into the master dark frame, and then that's subtracted from each of the raw images. And that's how I started out. That's what I did at first. I didn't do any of the flat frame stuff. I learned how to do this first and what results I got. For standard calibration, you do the dark frames, but you also do the raw flat frames and flat darks. So a master flat is needed for each set of light frames taken with a filter if you do multiple filters. Otherwise, you need one flat frame if you're doing like just a regular DSLR. And then advanced calibration with the other things you did before, then you create the bias frames and take that information out. So we went back, you have signal, which is the object you want to take. Noise is everything else that we just talked about to get rid of. So here's image calibration. Here's a raw image. And then here's dark frames and bias frames. Those are combined to a master dark. And here's raw flat frames, flat dark. Those are combined to the master flat. And all of that is done in the software, and you come up with a calibrated image. You have any questions about how we got to this point? So here's 120-second duration of the raw light frames. And you can see, the dark frame the dark frame pattern in here. You can see this light over here from the readout. You can see the vignetting. You can see dust donuts. And then if it's stacked and calibrated, you get a little bit better. So from the stacked and calibrated, now you want to remap the pixel values to bring out more detail in the image. So normally I use histogram shaping and brightness scaling tool. And again, it depends on the object of which one works best. So the histogram shaping brings out more detail in the image by redistributing the histogram to create more contrast between the available brightness levels. And I just mess around with it. I don't have any formula. I don't have any exact thing of how I do it. Same thing with brightness scaling. I just adjust it to bring out the image detail while adjusting the scaling range. And normally I use the linear, gamma, and gamma log transfer functions in AIP for Windows.
And this is all after you've applied the master and the bias and the flat.
This right. This is after it's stacked, calibrated, deconvoluted. Then I'm ready to do this histogram shaping, and this is what I come up with. So of the 4 filters. So this is after remapping. And to me, I always approach it like a trial and error because I never know with our sky conditions and everything else, what kind of raw images are going to come out of this stuff. So after processing the 4 images, register the images, which is register where the stars are so you can stack them on top of each other. So then I combine the 4 images into a color image. And depending on your processing software, such as PixInsight, etc., you'll have a different technique for each. So here's the final color image of the M51. So all the noise that I could was taken out of here. And if you can see it on your monitor, you can see this, really faint nebula around here. I don't know if you could see that. And
yes, it's visible.
Yeah, if I didn't do the flat frames and the bias and all that, I would, by taking that noise out, I would also take that signal out. So that's the benefit of the image calibration. So here's some other software. Here's Deep Sky Stacker. You see it calls for dark frames, flat frames, dark flats, offset bias. Here's Sequitur, so they ask for base image, noise images, vignetting images, and here's AIP for Windows, where it has bias, dark, flat, and a defect. So there's each software has this kind of thing in here, and I think the more you work your software, the better you get to know this stuff. And what I found was the more I knew about this part, the more I learned how to do the image acquisition. Like what will the sky give me tonight? What's the object? It took me a long time to figure out how to do globular clusters well.
Yeah.
With my CCD imager.
Yeah.
A long time. And then it took almost as long like to do bright open clusters like double cluster. And in fact, those are a little bit easier with DSLR than it is with the CCD.
Yeah.
But it's almost like you learn, you get into it, and then you work yourself backwards to learn the rest of it. So here's a screenshot from AIP. This is the raw file. And from this through the imaging, so that's where you saw that color picture of M51.
I have a question.
Sure.
How'd you create the FIT file?
It's saved like that in CCD Ops.
What's CCD Ops?
That's the camera software for the S-Big camera.
Oh, so your camera actually saves the FIT file as a normal
Yes.
result of the image?
Yes.
Oh, because I started reading the Handbook of Astronomical image processing, and now I'm learning about all these different file formats.
Yeah.
I had no idea about any of that stuff. It's
Yeah.
quite fascinating.
It is. It is. And,
Yeah.
and Greg, this is where, again, you kind of get into it and then you work yourself backwards. Okay, well, how can I benefit from this? And what can I do earlier in the process to make sure it works better?
Yeah. Most of my images have been using the software to darken the background. And like you said, I'm sure I'm losing stuff.
Right.
I did use dark frames and flat frames for my images of Comet Neowise. But it was clear from your image of M51 where you could see all the very faint nebulosity on the edge of the galaxy that you would just not be able to do that by trying to darken it with software like I do with Photoshop. So yeah.
Right. And you have to remember, like this is many years ago in my imaging age, but those were only 102 minutes. That's only 12 minutes. Just think if I did it the way I can do it now, when I'm better off with the guiding and everything like that, that I take an hour on each filter.
Well, okay, so that's one quick question is, how often do you revisit objects that you, like, when's the next time you're going to try M51 again?
Probably in the spring when it gets up high.
Okay.
Because it'll be high and it'll be after midnight, so everything will be really favorable.
I think Mark is spot on with that. And Greg, to address your question, yeah, you do things in your image acquisition and for some length of time, and then you process it and you think, oh, you know what, I could have done this. Maybe I should have shot more with this filter. And so I think the answer is, like, I'm already ready to go back to the Rosette Nebula.
Yeah.
That I did. I just did. I'm not doing it, but I want to, because there's so many other things to do. So you can always improve it. That's.
Hey, Greg, see the date I have in my file, 0409-2010.
Wow.
So this is quite a while ago for this example. But I wanted to give this example because I don't want to show the stuff that I'm a lot better at. This is the learning part of it that everyone needs to go through.
Yeah.
So anyway, here's the summary. Image calibration, you create a master dark frame, create the master flat frames for each optical setup. Process multiple image, calibrate and stack light frames. Stretch the images, register the red, green, blue, and clear, combine into a color, and then final calibration and color adjustment. So that final one is where you turn it into stuff where maybe you go into Photoshop or Corel or something and just tweak it a little at a time, right? Just little by little. So can you spot the defect in this image?
I see
This is the central.
Yeah.
This is a central portion of the Andromeda Galaxy.
Yeah.
Through the 6-inch RC6. So you see that dust donut there.
Yeah.
And I think what happened was that when I was processing this dust donut was so diffuse and there's so much signal in there, I didn't see it until after I tweaked it at the very end. So I would go back and pull all this out and redo it, except I already shot my flat frames. So I'm going to have to, find those flat frames wherever I put them on my computer and then try it again.
That's going to be my watermark.
Yeah.
What, the flat frame, the donut?
A donut, yeah.
Yeah. I should put in like FVAS or something like that, right? So here's another set of images. This is the Christmas tree cone and Fox Fir Nebula. This is a hydrogen alpha. I probably stacked 10 or 15. Who knows what I did? That's not the point. The point I'm trying to make is the one on the left is only dark frame. This one has the flat frames and bias and all that. Now, you see the center here is very bright versus this one. Some of the details washed out. That's because that center of my camera lens, I think I took this with a 400 millimeter lens or a 200, that center of that lens, the concentration in there. If you notice out here, the nebulosity is all the way to the corner, and it's much brighter over here.
In the upper right, it's really noticeable.
Yeah, this upper right here.
Well, the image on the left looks really grainy to me.
Yes,
Where the one on the right is very smooth.
yes. So these are the things that you get out of the mathematical reduction or the elimination of the noise versus what I would call the what am I trying to get? Not the software, the image processing software after calibration, trying to get that out. Does that make sense?
Mm-hmm.
This way I'm doing it physically. This one I'm doing it software.
Yeah.
If that makes a sense.
Yeah, I think to sum up, the more you can do before you start processing, the better your image is going to be in the end.
Yeah,
I see a lot more levels of contrast in the right hand.
exactly.
Well, frankly, it looks like you smoothed the data more on the right as well. It's not
Well, that's
just,
part right, but no, everything else was the same. I made sure that all the image processing was the same, except for you're taking that noise out, which allows you then, when you do go into the histogram and all that, now you've remapped the pixel values so that it's better distributed across what the signal is.
well, the major effect here is you by using the flat frame, you reduce the amount of vignetting.
Exactly, and that's an issue with the DSLR because your lenses are all going to have some sort of vignetting on them, right? Just
Well, it's a function of whether they're designed for, if you use a lens designed for a full frame camera and stick it on an APS-C, you'll see much less vignetting because the chip's smaller.
right.
But still, yeah, the difference is remarkable.
So again, these are the things that you go through trial and error. Hey, why is that way? Gee, I didn't know all these nebula were round like this. Well, they're not. Because your vignetting makes them look round. I was so excited at first. Wow, look at this. And then I realized.
Can you give a brief description of what deconvolution is, in case anybody doesn't know?
Yeah, let me get the definition out. So I don't want to say the wrong. Basically, deconvolution sharpens up the stars.
It takes a specified point spread function, which includes any blurring or distortion in the microscopic level, and it inverts the transform that it assumes that it started with a point and it became distorted, and it tries to invert that transform to go back to the undistorted image. And I'm talking distortion on the pixel level.
Does that have something to do with the Airy disk?
No, it's usually much grosser than that. The Airy disk on most of these images is quite small.
Right. Okay.
But it's trying to recreate the Airy disk. In that sense, yes, you're right. It's trying to recreate a point. So it sees a slightly blurred image, say it's slightly elongated ellipse, and it tries to estimate what kind of transformation would have taken a point and produced a smear. So it tries to invert that.
Is it related at all to any kind of wavelet adjustments?
No,
Okay.
no, wavelets are totally different. They're trying to do sharpening on a theoretically perfect image.
Gotcha.
So if you were going
Thank
to
you.
do that, you would do deconvolution followed by wavelet. Usually you don't use wavelet processing on deep sky because deep sky stuff is nowhere near diffraction limited
Right.
because of the long-term turbulence of the atmosphere.
Okay. Thank you.
Yeah, so basically, I'm reading out of the AIP book. Atmospheric turbulence, telescope optics, and mechanical instability account for pre-detection convolution. And so, like, your guiding is off a little bit and the atmosphere is not stable. Well, again, like Mark said, it makes allowances for that.
And
So it's
well,
like seeing
You can
condition.
overdo it too.
basically the convolution comes in because if you take a theoretical point source. And then you have all these nasty things happen like Mark described, atmosphere, guiding errors, that convolves it into a smear. So the deconvolution attempts, notice the use of the word attempts to invert that process and take it back to the original. It doesn't
Right.
always work perfectly, but under moderate conditions, it can help.
Right. And like in the AIP for Windows, you can go through anywhere from 4 to 8 to 16 to 32, 64 iterations. And the more you do it, the more contrast it's going to be. So, and Greg, if you look in that book, there's many examples of where they show where you over deconvolute and there's rings around the stars and
Yeah.
like the galaxy is like super granulated and detailed. So again, it's an art to figure out for your own image, how far do you want to go with that? The good thing is most of the time, if you save the image and you try it, okay, I don't like that, go back to the original, do it again.
Yeah.
A little bit more, a little bit less.
Yeah, if you have good guiding and good optics, you normally do not need deconvolution.
Right,
But there are times when it can save your butt.
right. Now, normally I go in and do 8 or 16 at the most. Every so often I'll need to do a 32. Richardson Lucy, but again, it's to taste and trial and error.
Yeah.
Okay,
Thank you.
16 watts.
I am going to
16 iterations.
iterations.
It's a mathematical